Hello, good evening everyone. Welcome to the NPTEL course on basic construction materials. Today we are at week 8. So we'll have a quick overview of the content of the week 8, and later we can have some discussions over the same, so that it will be helpful for you to solve the assignment problems. Okay. And I am Monica Mallela, and I am one of the TA for this particular course. I hope that all of you are able to see the screen. Already we have seen a few topics related to this. Now we'll go through the remaining topics. See, previously, like in the week 7 lecture, we have seen the aspects related to iron and iron products, and then steel reinforcing bars such as rebars used in concrete structures. And in that we have looked after this uncoated steels. I have looked after this uncoated steels. So this week we will concentrate on this coated steels, pre-stressed steels, and test methods and specifications, and then structural steel. Okay. And we have seen last week we have seen this iron and iron products such as pig iron, wrought iron, cast iron, etc. What are all the advantages and disadvantages of it, and what is the composition of it, and what is the purpose of steel reinforcing bars, and what are the different uncoated steels such as thermomechanically treated bars and cold twisted deformed bars, etc. And now we'll go through some steel reinforcing bars with some coating and pre-stressing steels, and the test methods and specifications for that particular steels. Okay. And where we'll be using those things. See, these are the things what we have seen in the last week lecture from 1 to 5. These are all uncoated bars. See, this is planed and ribbed mild steel bars. It is just hot rolled steel bars. And this is cold twisted deformed bars. Like we'll be making use of this quenching mechanism to make this cold twisted deformed bars. And then this is thermomechanically treated bars or quenched and self-tempered steel bars. This is corrosion resistant steel bars, and these are stainless steel bars. And in the coated steels, what we are going to see is, first one is fusion bonded epoxy coated steel bars, FBEC, and cement polymer composite coated steel bars, CPCC, galvanized steel bars, and pre-stressed steel bars. Okay. See, as you can understand from the name, these will all come under the category of coated steels. That means to the steel reinforcing bars we are applying some sort of coating so that it will be more resistant to corrosion, and it will have some advantages over the plain or some uncoated steels. Okay. See, the first one is fusion bonded epoxy coated bars, that is FBEC. The protection mechanism here is the primary cause for, the primary reason for adopting this coated steels is the main problem we are facing with the steel bars is corrosion. The main problem is corrosion. That's why in order to avoid that, that means in order to get some type of protection mechanism, we are going for these types of coated bars. Okay. So here in case of fusion bonded epoxy coated bars, how we are giving this protection mechanism is, see, for suppose this is the steel bar. Okay, you can see it in the gray color inside ring it is the steel rebar. Upon that, in the green color you can see some sort of coating, and upon that you can see some concrete. That means the bar will be embedded in the concrete, right? So there will be some layer of coating. This green color ring shows the layer of coating on the steel rebar. So by applying this sort of coating, we are able to do some elimination of direct physical contact between the metal and the electrolyte. What do you mean by electrolyte here? So the steel rebar will be in direct contact with the concrete, right? Concrete is an electrolyte. So by applying this coat, this epoxy coating, we are able to eliminate direct physical contact between the metal and the concrete, and the reduction in the driving potential by the protection film around the steel surface, and the reduction in the oxygen supply. Why the reduction in oxygen supply plays a major role here? Because the oxygen supply is the major cause for the corrosion of the rebars. That's why by applying this epoxy coating, we were able to reduce the oxygen supply to the rebar, and hence we were able to reduce the rate of corrosion to the steel rebar. This is the protection mechanism we can see in the fusion bonded epoxy coating, epoxy coated bars. Okay, see how we are able to achieve this FBE coating is, first the rebars will be blasted and cleansed and then heated. Okay, heated at a temperature of 220 degrees Celsius by the process of electrical induction or gas fired heater, and in this process it will be exposed to a mist of this epoxy. See why it is called as fusion bonded epoxy coating is, by the manufacturing process the name has come, that is fusion bonded. It is not like just applying a paint on the rebar. It is bonded to the rebar. It is bonded to the rebar. The epoxy resin is bonded to the rebar by the through the by adopting some different type of application process. Okay, the first step is blasting, cleaning and heating at a temperature of 220 degrees Celsius, and the second step is epoxy resin powder is ionized and attracted to the steel surface by the electrostatic forces. Okay, so the steel surface will attract the epoxy resin powder. Okay, and then water quenching results in a thermosetting polymer. See, uh, after this second step, if you don't go for this quenching process, quenching is nothing but by the second already the rebar will be heated up. Okay, to reduce that heat we will be immersing it in water. It will be dipping the rebars in the water. So water quenching results in a thermosetting polymer. Because of this quenching process, because of this water quenching process, the epoxy coating will be bonded to the steel bar, bonded to the rebar. Okay, and after this it will be inspected for holidays or damage. Holidays or damage is nothing but, see, you can see that in the next slide. It is nothing but the black macro openings which allow water and oxygen molecules to enter through the coating and lead to underfilm or crevice corrosion. See, in the microscopic level, you will be able to see some black micro holes or openings on the surface of the epoxy coated bars. Okay, what will happen if we have some sort of openings? See, the prime reason we are applying this coating is we want to uh, avoid the ingression of water or oxygen on the steel rebar. So if we have these openings, what will happen? The ingression of water and oxygen molecules will happen over the surface. Through if the ingression of oxygen and water molecules reaches this steel rebar, what will happen? It will corrode the surface of the steel rebar. It will be a localized corrosion, because only a small part of the small part of the rebar will be exposed, right? So at that location you will have more corrosion action, that is localized corrosion can happen at the surface of the rebar. Okay, and in case of this fusion bonded epoxy coated steel rebars, what we can say is, see, you would have seen some normal steel rebars. You would have seen some bending process at the construction site, like the steel rebars will be bended to make use of it as stirrups, etc., at the corners of the, like at the corners of the beams and columns, right? So but in case of this epoxy coated steel rebars, hot tools will damage the epoxy surface. Hot tools will damage the epoxy surface. That's why at the site we can't bend these epoxy coated steel rebars. But prior to the coating itself we have to bend it. Prior to the coating itself we have to bend it. And see, additional epoxy is simply applied at the site. See, after bending, since the due to inadequate ductility, the epoxy coating can crack during the bending at site. See, if a straight bar is taken and if it is bent at the site, what will happen? See, there won't be enough ductility. It will be of brittle nature. The coating will be of brittle nature after drying, right? So due to inadequate ductility, the epoxy coating can crack during the bending at site. So if you bend it after the coating is applied, you can see some sort of cracks over here. Okay, so because of the cracks, if an additional coating, like an additional coating is applied at the site at ambient temperature conditions, like ambient temperature will be less when compared to the like we have done this fusion bonding epoxy coating at a temperature of 220 degrees Celsius, where we can't find the temperature, like at ambient conditions we can't find that high temperatures, right? So when you apply this additional coating at the ambient temperatures, the fusion bonding will not take place. See, fusion bonding will not occur at the ambient temperature condition, so additional layer is not repairing the damage and is not in contact with the structural steel. Okay, so it is of no use. So additional epoxy coating using simple paint brush at ambient temperatures does not lead to fusion bonding and it should be avoided. So for this reason we can't do bending of epoxy coated steel rebars at the side. Before the coating itself we have to bend the rebars. Okay, see, and the another problem with the epoxy coated steel rebars is if it gets exposed to the like steel rebars gets exposed to the UV during storage and delays in construction. For suppose see, if you want to use this epoxy coated steel rebars and like at the like you'll have a plan of the construction schedule will be planned aforehead, right? So based on that you can bring this epoxy coated steel rebars to the site and you can use it. But if there is some delay in the construction process and if you get the steel rebars like epoxy coated steel rebars to get exposed to the UV radiation, then it will result in premature corrosion initiation. So the purpose will not be served here. The premature corrosion initiation will start if it gets exposed to the UV radiation. And see, mechanical damage and UV attack can happen to coating and can result in premature corrosion initiation. See, poor quality FBE coated steel rebars are being used in many projects. See, uh, uh, in most of the constructions we won't go for this. In our country we won't go for this epoxy coated steel rebars because you will have like UV exposure will be more because the temperatures will be more here. And if the coating is not if the bar is not properly coated with the epoxy, then premature corrosion initiation will happen. So when you compare, like if you can't avoid these conditions at the site, then it's better you do not go for this epoxy coated steel rebars. Instead you can go for uncoated steels, because coated steels should be used at some particular conditions and with due care. Okay, see, you can see at microscopic level the image here in the left hand side, the image here shows before UV exposure, day 0. So at day 0 there are no cracks on the surface, but significant cracking after 2 months of UV or sunlight exposure. See, this is a picture taken on the day 10. See, the red lines here, you can see the cracks over the surface. So chlorides or moisture can penetrate through these cracks and initiate corrosion at an early stage. Like the disadvantage of having these cracks on the surface is they will initiate corrosion at the early stage because of the ingress of water and oxygen. Okay, and see, with scratched or damaged coating, crevice corrosion can happen even without chlorides. Even there is no exposure to chlorides, but the surface is scratched or damaged, then also the corrosion will take place. Chloride concentration at rebar level was approximately 0.2%, which is less than typical chloride threshold of the bare steel. See, in the absence of presence of damage, moisture induced corrosion can take place. This can happen even without the presence of chlorides. Okay, so it is very important to reject the damaged FBEC steel bars. Okay, that is the main motto now. Okay, so see, this fusion bonded epoxy coated steel reinforcement, like it can be available in straight and bend bars, but only thing is the bending should happen before the coating itself, and bars must be bent before epoxy coating. And check for holidays on the bar surface. Holidays are nothing but the black micro holes on the surface, and multiple layers of epoxy coating, and the epoxy coating should be fusion bonded epoxy coating. Okay, so see, this is the steel and this is the FBEC, and if you have some kind of opening or some kind of black holes or holidays or damages uh, on the surface of this epoxy, then what will happen? Through that holes, the moisture will go through go to the reach to the surface of the steel, and the corrosion can happen. So there is no active protection. So then it is not serving the required condition. So it is more dangerous to use damaged epoxy coated steel than conventional uncoated steel. So that's what I told you. Like uh, instead you can go for some uncoated steel. If you are not able to maintain the proper conditions at the site, then it's better to go for this uncoated steel instead of going for this epoxy coated steel with damages, because there will be localized corrosion at the surface of the steel rebar, which is very dangerous. Okay, see, premature corrosion can happen due to moisture attack even without chlorides. Okay, even there is no exposure of the steel rebar to these chlorides, then also if the bar has some damages or black holes, it then premature corrosion can happen. Okay, so this is all about fusion bonded epoxy coated bars, steel bars. And the next thing is cement polymer composite coating, CPC coating. And here the manufacturing process is, it is in 3 steps, as you can see in the figure. The first step is first uh, clean and make the surface rust free, and this is the uncoated steel surface. Okay, so how we'll make it as rust free? By sand blasting the steel surface. That means on the steel surface we'll be applying sand with some force. Okay, so rust free sand blasted steel surface provides large surface area to bond. Okay, see, if it is rust free, there will be the surface area will be more, and the bonding will also be more, and chemomechanical bonding between steel and coating will be very good at this, if you make it as a rust free. And the second step is CPC primer coating. So you will be applying some coating of primer, like cement with acrylic polymers as additives. Okay, so as you can see from the name, cement polymer composite coating. So cement will be mixed with some acrylic polymers as additives, and then applied on this surface of the plain steel, like uncoated steel surface. So cementitious content helps to form a passive film on surface steel. Okay, passive film. Passive means, that means it will be inactive for the corrosive environment. Okay, and it adheres well with the steel surface. Okay, and then CPC seal coat has to be applied. So cement with acrylic polymer as additives will be applied again, and it is available in different colors like green, gray, etc. Okay, see, mechanism here, like in case of FBEC steel bars, we have seen some mechanism, like how we'll be protecting the steel rebar from corrosive environment by applying the epoxy coating. Here the mechanism is provides alkaline environment to the steel and helps in the formation of passive film. Like by applying this cement coating, then you can there is a formation of passive film which will be helpful for the corrosion resistance to happen. and then elimination of direct physical contact between the metal and electrolyte, same as the case of FBEC bars, and reduction in the oxygen supply. This is the mechanism for the corrosion prevention will be the same here, but the material used will be different. Okay. Here also the same thing. If there are some damage for this coated steel rebars, even if it is a CPC or FPEC, whatever it is more dangerous. Okay, because it will attract more corrosion. Okay, and till the two things we have seen is FBEC and CPC. They are some epoxy based coatings, but here this hot dipped galvanized steel reinforcement HDC is it is metal coated. It is metal coated, not epoxy coated, and we'll see how this the process, how the manufacturing process is here. And ASTM A767 gives the standard specification for zinc coated galvanized. Here is it is zinc coated. The steel rebars will be zinc coated for use as a concrete reinforcement. Okay, and IS 12594, the hot dipped coatings on structural steel bars for concrete reinforcement specifications. Okay. Here the steel rebars will be immersed in this zinc bath, like it will be put it put it in zinc bath at a temperature of 450 degrees Celsius, and then it will be cooled and then inspected for some damages or holes. Okay, so this is the hot dipped galvanized steel reinforcement. Okay, this is the manufacturing process here. See, zinc bath at 450 degrees Celsius, iron zinc alloy layers. So when you take this when you immerse the steel rebars into this zinc bath at 450 degrees Celsius, what will happen? Iron zinc alloy layers will be formed and more abrasion resistant than the non-metallic coating. This is the major advantage when compared to the non-metallic coatings. You will have more abrasive resistance because the non-metallic coatings are not abrasive resistant, because when you have some abrasion happening on the surface, the coating will be will come off. The coating from the surface will come off. So there is so the non-metallic coatings are not abrasion resistant, but here as it is a metallic coating, it is more abrasion resistance, and no special handling is required because it is not a coating to get out of the surface. So no special handling is required. See, at the microscopic level you can see the iron is coated with this zinc. Okay, the coated with this zinc. Okay, and see, the another major advantage of this galvanized coating is even the corners, even the sharp corners, sharp edges will be covered, not as the case of like it won't be the same as the case of this uh, non-metallic coatings. For non-metallic coatings you can't reach out to this sharp edges or surfaces. Okay, so but here in case of this galvanized way, good coating can be achieved even at corners, edges or tips. Okay, that is another advantage of this. Okay, so when we look at the few features of this, like zinc has higher chloride threshold than steel. That means 2 to 4 times more than steel. For suppose if you take plain steel rebar, when compared to the plain steel rebar, this hot dipped galvanized steel reinforcement will have more chloride threshold. That means it needs 2 to 4 times the amount of chloride to get corroded when compared to the normal steel, plain steel. Okay, and another thing is zinc has much lower pH threshold than steel. So when it has lower pH threshold, what will happen is there will be, we can see, better resistance of the particular bar to carbonation induced corrosion, like chloride induced corrosion and carbonation induced corrosion. There are two types of corrosion here. So in both the cases, this hot dipped galvanized steel, because of this zinc coating, will be useful in both the conditions. Okay, and the corrosion rate of HPG steel is considerably lesser than that of the uncoated steel, and high abrasion resistance and good corrosion resistance makes the type of bars a good choice for durability. And costlier than the normal non-metallic coated rebars or uncoated rebars. But you can see this point. See, consider life cycle cost instead of capital cost. Even the capital cost is higher, but the life cycle cost will be more effective. That means it will have higher lifetime than the normal uncoated bars. Okay, see, as example, this is a in Chennai East, you can like you would have come across this place Mahabalipuram. At that Mahabalipuram you will have a shore temple. Okay, so which would be only a few meters away from the shore, so it will be more prone to this sulfates and chlorides. Okay, so here in the construction of this particular temple, they have made use of this hot dipped galvanized steel reinforcement because it has more abrasion and corrosion resistance. Okay, and this is the typical cost comparison of steel rebars. That means this conventional uncoated steel, when compared to this conventional uncoated steel, this epoxy coated steel will have 33% more higher cost, and the galvanized steel will be double the cost, and the solid stainless steel will be 6 to 7 times the cost of the conventional uncoated steel. But what we have to consider here is this life cycle cost instead of the capital cost. Okay, this is another type of this rebars, like pre-stressed steel strands. See, why we are going for this pre-stressed steel strands is, like when you have high-rise buildings or some long span bridge construction, when you have some huge structures which are of utmost importance, then we have to go for this pre-stressing steel strands. Why it is mentioned as steel strands instead of steel bars is, it is a it is a combination of some number of bars, like some 6 to 7 bars, 6 to like 7 or some 3 bars, 7 or some 3 bars will be bonded together, like not bonded, it will be uh, stranded together. Stranding means is nothing but tied together. Okay, it will be tied together. Okay, see, this is the 7 wire strand. That's why it is known as pre-stressing steel strands. It is a 7 wire strand, and on that some grease. This coating is nothing but some grease coating will be applied, and sheathing is nothing but some hollow pipes. Okay, hollow pipes. This is how it will be made, and this will be made as like coils of large like huge lengths, because for suppose if you go for some construction of flyover, okay, then you require higher lengths, right? You require higher lengths, so that's why it is made like this instead of cutting it into some uh, meters or centimeters. Okay, and see, it will have higher strength. Suppose the strength will be uh, 1860 megapascal. The yield strength here will be 1860 megapascal, so approximately it is 4.5 times more than the normal steel. Okay, and it has low relaxation and necessary for long span construction, cable stayed suspension and pre-stressed concrete applications. These are the applications like cable stayed bridges and suspension bridges. There you can see the usage of these bars, these strands, and unsheathed and sheathed strands both will be, this is unsheathed and this is sheathed, and the number of wires will be different. For suppose I have here the number of in this strand, the number of wires is only 3, and it will be used in making of this sleepers will be there, right? Like on the railway tracks, these are the sleepers. You can see the concrete sleepers here, and for making of these concrete sleepers, inside these concrete sleepers you can embed this 3 numbered wire strands. Okay, 3 numbered wire strands. Okay, so this is the application of 3 numbered wire strands, and this is steel strand, how it look like. Okay, and this is some cable stayed bridge. Okay, and strands are supplied in coils. Why? Because we need it in higher lengths. The higher lengths will be more where we'll be using these strands. That's why it will be supplied in coils. Okay, So large infrastructure systems are built using these high strength steel cables and strands, like in metro constructions or elevated highways and flyovers and bridges over seawater and power plants. Okay. These three wide strands are used for railway sleepers. That's what I told you earlier. See, these are the pre-stressed steel strands with three numbered wires. Okay. And this is another type, that's pre-stressing steel reinforcement with threaded bar, and this will have some other applications like a high tensile alloy steel bar which features a coarse right hand thread over its full length. Like these will have major applications in some construction of tunnels or some slope embankments, etc. Okay. And you know this stress strain diagram of metals in tension, you know how it would be. And you know what is the nominal stress and true stress, because nominal stress is initial cross section area. When you calculate the stress, it is known as nominal stress. And after the reduction, like after applying the tensile load, at this point you will see some necking region. That means there will be a reduction of diameter, thereby the reduction of area of the bar. So here if you calculate the stress, it is known as true stress, and this is the proportional limit region or elastic region, where you can find the elastic modulus, and this is the yield stress, and this is the ultimate strength. Okay. And there are some IS specifications where you can see this IS 1786. Here you can see the high strength deformed steel bars and wires for concrete reinforcement specification. So specification for high strength deformed steel bars and wires for concrete reinforcement can be seen in Indian Standard 1786. So see, this is a table from this code that which consists of the mechanical properties of high strength deformed bars and wires. Okay. This table consists of serial number, property, and property of FE415, FE415D, FE415S. Okay. So what does this number represent? This 415. We have already discussed earlier in the earlier lectures, right? So the number represents the specified or design yield strength, or nothing but the characteristic strength of the steel. Okay, the number represents the characteristic strength of the steel, whereas the alphabet D represents the enhanced ductility. That means Fe415 bars with enhanced ductility, that means with enhanced specified minimum percentage elongation. Okay. And the alphabet S represents the enhanced strength ratio, that means the ratio between ultimate stress to the yield stress. Okay. See, you can see the property is 0.2% proof stress or yield stress in Newton per mm square. That is the minimum value. The minimum value is nothing but the yield stress will be the same as this. This 415 is nothing but the characteristic strength. That means here it will be 415. In these three cases it will be 415. Here it is 500 in these three cases, and here it is 550, and here it is 600. Okay. And this table shows the influence of different chemical ingredients on properties of steel rebars, like the different chemicals like carbon, manganese, sulfur, phosphorus, copper, etc. And what are all the effects of this composition on this rebars, like controlling property when it's suitable concentration. See, hardness, strength, weldability, and brittleness. Carbon will have effect on this hardness, strength, weldability, and brittleness. Okay. So less than 0.1% carbon, when the carbon is less, it will have reduced strength, but when it is in more, like greater than 0.3% carbon, it will be unweldable and it will also be brittle. We know that, right? Like the increase in carbon percentage will give an increased strength, but it will give a lesser ductility. Okay. And manganese affects the yield strength of the rebars. Sulfur affects the brittleness, whereas phosphorus affects the strength and brittleness. Okay. So these are the different chemicals which will have the effect on these rebars. Okay. And what are all the requirements here? So here for Fe415, the carbon content, the maximum it should not be more than 0.3%, sulfur should not be more than 0.06%, phosphorus should not be more than 0.06%, sulfur and phosphorus should not be more than 0.110%. Okay, these are all the different compositions. And see here, these are the available nominal sizes and the cross sectional areas, and this is the mass per meter in kgs. Okay, these are all the different sizes which are available, and here the nominal size is nothing but like the diameter will not be exactly equal to the 4 mm, but it is a rough idea, like a value existing in name only but not a real value. These are all the different definitions for what is meant by nominal. Okay, like see here it is mentioned as the nominal size is 4 mm, that means the diameter of the bar is 4 mm, but if you measure it, it won't be exactly equal to the 4 mm. There will be some like it would be around some 3.8, something like that. Okay, and coming to the different types of test conducted is here bend test. This is one of the test conducted, and the Indian standard specification for this is IS 1608. So specimen considered to pass the test if there is no crack or rupture. So when you do this bend test, and if there is no crack or rupture on the surface of the bar, then we can say that it passed the bend test. Okay, and see mandrel diameter for bend test. There is a table for specifying the mandrel diameter for the bend test. And what do you mean by the mandrel? See, this is the mandrel here, this is the mandrel here. This will be used for bending the bars, this will be used for bending the bars. Okay, and why there is some specification for the diameter of this mandrel is because, see, if you use some lesser diameter mandrel, what will happen is when bending the rebars, there will be some sharp formation of sharp edges, and thereby yeah, like the test will not be appropriate. That's why for mandrel also there are some specified diameters. Okay, from the IS specifications. And see, these are the important tests which we need to conduct on the rebars: tensile strength, yield strength, elastic modulus, elongation. All these you can get from the stress strain diagram. You can see all these things. And TM ring test for TMT bar, that is thermomechanically treated bars. In the last lecture you have seen this ring test. And for coated rebars, we need to test it for abrasion resistance and coating characteristics and peeling off resistance and cracking resistance. Okay, these are all the important tests we have to take on the rebars. Okay, this is the case of the like this is in this lecture what we have covered is this coated rebars, in which few things we have seen related to this non-metallic coating, and the few things we have seen related to the metallic coating, and what are all the different tests we need to conduct on this particular rebars. Okay, so this is one of the topic in this week's content. And the other topic is we need to see about this aluminum and copper. These are another like one of the metals which are available, aluminum and copper, and what is its manufacturing process, what is its composition, and what are its uses, we can see in this lecture. See, this is the production of aluminum, and the raw material for the manufacture of aluminum is bauxite. So this bauxite will be poured into this crusher, and water will be sprayed on this, and it will be dried in some kilns, and then this crushed bauxite will be taken to the mixer, then digester, then settling tank, and then it will be passed through this cooling tower precipitator, and then it will be calcinated at some temperatures in a kiln, and then you can get this molten aluminium, and this molten aluminium can be transferred into the casting molds. Okay, this is the manufacturing process of aluminium. And how the aluminium is produced is, first alumina is chemically extracted from the bauxite. So from bauxite, first alumina is extracted from the bauxite. and alumina is nothing but a mixture of hydrated aluminum oxide, that means Al2O3 with some hydration, and hydrated iron oxide. Okay, then alumina is reduced to aluminium. How it is reduced to aluminium is a smelter requires of about 1350 DC kilowatt hours of electricity to produce one ton of aluminium. Okay, see, if you can see here, the raw material here is bauxite. So when you take 4 to 5 tons of bauxite, then you can only produce 2 tons of alumina from that, and out of that 2 tons of alumina you can only get 1 ton of aluminium. So, and a lot of red mud you can obtain as the byproduct, but red mud is of no use actually. Okay, so that's why aluminium is very costly, because a large amount of raw material is required uh, to obtain a smaller amount of aluminium. Okay, and see, in Orissa, the red mud, this is the red mud pond. Okay, so for every ton of alumina produced, the process can leave behind a third of a ton to more than 2 tons of red mud. Okay, more than 2 tons of red mud. And see, this is here the lots of red mud in Orissa, which is in rusty color from the presence of iron compounds, and it will have very high pH. So if the lake comes, like if there is no protection walls or bunds, then it gets leaked, and with very high pH, and it will be very dangerous. And now and a recent innovation which is going on is this red mud is getting used in this road construction work. It is in the I think it is in the research stage. Okay, and aluminium, as we see, it will be like you would have observed in some kitchen products or some packing products and an automobile industry. It will be mostly used for making of containers, packings, aircrafts and automobiles. And in civil projects we will not be using it as a structural member, but for architectural purposes like finishing of doors, windows, sliding doors, etc. Okay, and here the by why we are not using it as a structural member is cost wise it is very high, and strength and ductility wise it is less compared to the steel, and the coefficient of thermal expansion of steel is equal to the coefficient of thermal expansion of concrete. That's why we are using steel as the reinforcement for concrete, but here for alumina the coefficient of thermal expansion will be different, so we can't use it as a reinforcing element. And this is anodized aluminum. It is one process of aluminum wherein you can get different colors of aluminum for aesthetic purposes. And the advantages are, it will be most plentiful metal on the earth. It will be available in uh, most plentiful metal on earth, and it has one third the density of steel. That means the weight of the aluminium will be very less, and it has high strength to weight ratio and high corrosion resistant. Because why it has high corrosion resistant is, see, this is the aluminium and it will be covered with aluminium oxide, and this aluminium oxide will not allow this oxygen and water to pass through this, and it will be used that's why it has some high corrosion resistance. But in case of iron, this iron oxide is this iron oxide cannot stop the ingress of water and oxygen, uh, so the water and oxygen will reach the iron product and it will get corroded. So high corrosion resistant, good thermal and electrical conductivity. So these are all the advantages of aluminium: ease of maintenance, ease of fabrication, etc. And this is the stress strain behavior of aluminium. Through that we can find what is the modulus of elasticity and what is the ultimate strength. See, here the ultimate strength is 100 to 550 megapascal. Okay, and modulus of elasticity is 70 to 79 gigapascal. And when you see the effect of temperature on the strength of aluminium, as the temperature increases, the strength of the metal will decreases. That way it will have some limitations at some particular locations. And the cross sectional dimensions, see here what what we want to depict is, see the cross sectional dimension of steel and aluminum bars considering equal deflection. For suppose if you take a bar, a beam, if you take a beam which is centrally loaded with a point load, okay, and for a simply this is a simply supported unit. So the deflection for a simply supported beam with central point load is WL cube by 48 EI. Okay, here the length is taken as 2x and the dimension is height is h and width is b. So delta is equal to WL cube by 48 EI. L is replaced with 2x. Okay, and in case of E and I, we can replace it with the properties of aluminum and steel. See, this is W L cube by 48 EA IA. That means elastic modulus of alumina and moment of inertia of alumina. Okay, then this is for the case of steel, and when you equate it, what you will get is EAIA is equal to ESIS, and this is a rectangular section, right? So BH cube by 12. So see, for suppose if you take the height of the alumina and steel cross section as same, and ES value is 200 gigapascal, EA value is 75 gigapascal, then you can see the width of the aluminium required for the same deflection is 2.7 times the width of the steel. That means higher sections are required for aluminium. Okay, for aluminium higher sections are required. That's why it is not advisable, but because in cost wise it is not beneficial. Okay, and these are the some properties like specific gravity, melting point, etc. And this is the anodizing process. Anodizing process is the process of coating the aluminium with thick layer of aluminium oxide, uh, because of which we are able to go for different colors of aluminium. Okay, see, this is one type of anodizing process, that is silicon carbide mold is used to make ordered array of convex dimples in aluminium surface prior to anodization. See, before anodization, what is the process is, this is a silicon carbide mold, and this mold will be pressed onto this aluminium metal, and it will make some undulations on the surface, and on in these undulations you can pour the dye, like in which color you want the specimen, in that color you can dye it. Okay, and this is a graph for this between wear cycles versus the thickness, and hard anodizing is the longest wearing of all these options. Like when you this hard anodizing, this is hard chrome plate, these are the different types of anodizing process. Like when you consider this hard anodizing process, then the aluminium can resist more wear cycles. Okay, some number from thousands of wear cycles can be resisted by this hard anodizing aluminium. And when you come to this uses of aluminium foil, like in abroad you can find it, like this aluminium foil can be used as an insulation for buildings, because it will have more reflection, like reflective insulation system works by reflecting radiant energy, so the UV light will be radiated back. It will not be uh, it will not pass through the building. Like aluminium foil can reflect up to 97% of the radiant energy, and reflective foil insulation is composed of, how it will be made is, it will be like a sandwich material, like two outer layers of aluminium foil, in between an inner layer of some inert material, say polyethylene or plastics or fiberglass, etc., to create the required air gap between them, so that the radiation effect will be uh, good. And this is an experiment showing this aluminum insulating capacity. See, this when there is no coating of insulation of this aluminum. Then uh, because of the uh, increase in the temperatures, the surface is also increasing. But when you see here, see, as the experiment depicted above shows, fiberglass is ineffective at stopping radiant heat, but the reflective foil redirects the intense rays from the heat lamp and keeps the chamber cool at 78 degrees Celsius. Even at 78 degrees Celsius, the chamber is cool here because of the reflective nature of the aluminium. But when you use this fiberglass alone, there is no reflective nature, so it is getting heated up when the temperature increases at 78 degrees Celsius, at 107 degrees Celsius. Okay, aluminium formworks, because aluminium is used in formwork because it has lighter weight. And when coming to the copper, India is not a major producer. As you can see in the pie chart, Chile, China and Peru, they are all the major producers of the copper. And mainly the ores used in copper are mainly oxide and sulfide ores with only 0.5 to 2% copper. So that's why copper is also more costlier, because the percentage is very less here. So about 80% of global copper production is extracted from sulfide sources. Okay, from sulfide sources 80% of the global copper production is based. And copper and its alloys, why, where they will be used and what are the advantages, is because of high resistance against atmospheric corrosion. Copper is used in buildings along the coastal regions and industrial areas, and traditionally it is also been used in temples, roofs and ships. Okay, see a typical temple roof in Kerala, this is an example where copper is used. And when you go for this copper and its alloys, uh, um, see, copper is used in electrical cables and plumbing works, and the alloys for the copper are brass and bronze. Brass is nothing but an alloy of copper and zinc. Bronze is nothing but an alloy of copper and tin. And the advantages of copper using in plumbing is, like, it is a relatively soft material. So when the material is soft, you can easily bend it or cut it, and bacterial growth is less than the plastic pipe. See, in case of plumbing works, for suppose if you have to fit some pipe at the sink, if you take the plastic pipes, the bacterial growth is higher in case of plastic pipe, but in case of copper, the bacterial growth will be less, and it has more corrosion resistant and then durability. It also have UV resistant and temperature induced variations. For suppose if you take plastic, when uh, when higher temperatures or some fire etc is there, it will melt. But in case of copper, fire will not have any effect on the copper, and no release of toxic gases upon burning. See, when you burn plastic, there will be release of toxic gases. So here in case of copper, it won't happen, and it is recyclable. Okay, and disadvantages are, we have to check for the acidity of water before using it in plumbing works. Okay, so this is an overview of the like aluminium production properties and uses, same as copper production properties and uses. So in this week we have covered two topics. First topic is this coated steel rebars, and the other topics are other metals such as aluminium and copper. Okay, so we'll meet in the next week with week 9 content. Okay, so if you have any doubts in this week content, you can feel free to ask now. Any doubt in this week's content? Okay, I'm stopping the session for today. We'll meet next week for the week 9 content. Okay, thank you for listening.